All right. So, of course, today we were looking at lists. It seems like it was pretty easy, right? So let's talk about it a little bit. Lily, what did this first program do?
I'm sorry.
Lily, yeah.
Oh, Lily, my bad.
It's okay.
Okay. This program, I forget. We didn't. That wasn't the. Okay, I have to recopy it into the REPL. Can you maybe ask somebody else?
All right. Yeah. Leon, you were talking. Can you tell us about this function this program right here?
Sure. So, so this function, sorry, I'm trying to pull up the document. So this function basically took just printed out a random list of numbers.
Is that all? So clearly here, these lines here, it's making a list of numbers, and the numbers are between 1 and 1,000, right? So as we go through this loop, we're making a random number and we're adding it to my list, right? So we go through this loop over and over again, and we make a list of numbers, right? And in fact, if I go over here, you guys are seeing my screen, right? So if I print out just my list, I don't call the function, let's run it, and we get a bunch of numbers between 1 and 1,000. We get 100 numbers, but they're in random order, of course, because we generated them randomly. So we create this list. Now, if we call order list as a function and we pass the list to it, my list goes into new list, what does this do? Well, first it sorts the list, and then it reverses the list, and then it returns this revised list. And so now if we run it, we see that the numbers are in sorted order. We get a different list of numbers every time I run it, but they're all in order, right? So sort took those numbers and put them in order. But now, what did reverse do? Let's take it out. What does reverse do? Anybody? Joe, do you know what reverse does? Or no, somebody was answering. Yeah, go ahead.
Reverse puts it from largest to smallest, or in the reverse order of the sort.
Right. It takes whatever order sort put it in, and it turns out sorts, we use the term ascending by default. In other words, it ascends from small to large. That's what sort does. And reverse just takes it. So that's pretty nice. So we can do things so quickly, right? So I can really easily make a bunch of random numbers, which, by the way, can be useful if we're doing data analysis, right? We might need a bunch of random numbers for something. And then I can just use a single line to take a list and sort that list. I can use another single line to say, take that list and reverse that list. And then this function, right, is a nice little function that takes and makes the list an ordered list. All right, so wait, is that where we wanted to go? So Phineas, what does the alpha function do?
It checks if a string contains letters and it outputs a Boolean. So it's true if the string contains only letters.
Right. So what if it's mostly letters, but it has a few other things in it?
Then it'll be false. I think it has to be all letters when we
Right.
did it.
So this allows us to see, is everything in the string alphabetical? What if there's a space in there? Did you try that?
I'm not sure. I don't know. I don't think we did try it. I'll have to.
Well, let's try that real quick here. This is the beauty. We can try things out quickly. Enter a string. So let's put in Kenyon space college. Does not contain all letters because Kenyon space college contains a special character, a space, right? Interesting. Aiden, what does this program do?
That program checks to see if the input is a digit, and if it is, it prints the fourth power of the digit or input that you give. And if it's not, it says it's not a valid number.
So what are some of the other things that you put into it that didn't work? Like what if you put in 2 digits?
2 digits worked, but
Okay.
strings, or not strings, like characters don't work.
What if you put a space in there?
Don't think we tested a space.
That would have been a good thing to test, huh?
Yeah.
Let's try that. So here it is, enter a number 4 space. It's not a valid number, right? Right, so we can't put, it's gotta be only numbers. That's a big number. Python can do pretty big numbers. Look at that. They do really big numbers. That's a really big number, right? What if we do a really, really big number? Can it do it? Turns out that Python, that's just a super big number. And look at that. It's even bigger. So one thing about Python, and many programming languages don't have this feature. Many programming languages, the numbers have a maximum size for an integer that's big, but it's not this big, right? So, but Python is designed to basically have almost infinite size numbers, right? As long as you want to take the time to generate them and such. All right. So then, let's see who I'm going to talk to. Achilles, what did this program do? Number 4.
This program basically just counted the number of spaces in a sentence.
Right. So it goes through it goes through the sentence one letter at a time, and every time it sees a space. And so what does is space do?
Checks if the specific index there is empty, I guess.
Right. Right, if it's a space, right? Space is actually a character. It's not really empty, right? It turns out the only emptiness you can have in a string is if you literally have a string that's a quote, quote, and then the string is empty. But a space is something different. A space is actually a special character that that leaves a little bit of space, but it doesn't print anything other than it leaves a gap, right? It's like a character without any pixels. All right. So back to Lily. What did we've already seen this before, but what did this program do? For which one of these was it correct?
For us, it was correct for all of them except for CMSC 180.
Right, because that's actually different, isn't it? But the rest of these, and of course, we're seeing this a lot. When we do this word thing, and when we did Emily Dickinson, right? We see that we can sort of normalize things, and that's a term that we use, normalize, to make it easier so that we don't have to type in exactly the same thing. It turns out that email addresses are like that, right? It turns out email addresses, it doesn't matter whether you make things lowercase or uppercase, it just converts it to lowercase anyway. And that's good, because otherwise, wouldn't it be frustrating if you had to say, okay, no, my email address is capital something, lowercase, capital something, right? We don't have to worry about that, because that was frankly a smart decision that the people made decades ago when they decided what an email address was going to look like. Now, it turns out, of course, variable names, capitalization matters, but oftentimes when we're working with people, we want to sort of factor that out or normalize the data. Phineas, what happened here on number 6?
1 second. So we said that we thought it was going to print. Yeah, we thought it was going to print cat at first, but it actually prints hat, and then there's an error message. And then we found out, as it says below, that strings are immutable, so you can't replace letters within a string.
Excellent, yes. So here's the thing. A string kind of seems like a list because we can index in it just like we can do an index on a list. But a string is different because it's immutable. Once you make a string, you can't change it. You can build a new string using pieces of the old string, using slices and stuff, but you can't actually change a string once it's been made. It's immutable, never changeable. All right? And that's okay, because it's easy enough to make a new string from pieces of an old string. And that's why we looked at these slices here, right? What did the -2 do, Phineas?
-2. Oh yeah, it printed the lowercase I.
Right. Why is that? What's -2 mean?
It means it prints the lowercase I from the last word logic, so it goes from behind.
Right. So it's basically saying starting at the end to count backwards, right? And so C is -1, I is -2, G is -3, O is -2. Aiden, what does 0 through 13 do?
That printed out the word introduction.
Right, because it takes those 13 letters and that's it, starting from 0 to 12, right? And that doesn't go to 13. It actually, this means start at 0 and stop just before 13. And then this, what did this print, Haley? Or yeah, I guess Haley wasn't a spokesperson, but the
16 to 27, that points out, and that prints out prints out the programming.
all right, it just grabs this, right? And what did 28 colon do?
Sorry, 28 colon printed out just printed out the logic, the last word.
Right. So when you leave it blank, what does that mean?
When it's blank, it just means like 0, like kind of like it's just kind of, it's like just the end, right?
I mean, Achilles, do you want to comment on that? Does that mean 0, or what does it mean?
So if there's nothing there, it just goes to the end.
Right. It just means go to the end, right? And it turns out you can leave a blank at the beginning, and that means start from the beginning and go to here. Now, here's where I want to show us something kind of interesting that's sort of inferred later. What if we say this? L1 is equal to, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now we have a nice little list. If I say L2 is equal to, for example, L1, we can do this with, we can do this with strings, but we can also do it with lists. 2, 6. What do you think that's going to do? Let's print L2. Any ideas what that'll do? Let's see. If we go 0, 1, 2, it should start at 3, 3, 4, 5, but then stop before it gets to the 6th one, which is the 7. That's not confusing, right? So we can slice an array as well. In fact, we can do stuff like this. I can say take from 2 to the end, right? 3 to 9, or I could say take from the beginning to 5. And there's the beginning to 5. So we can slice strings, we can slice arrays and make smaller ones. Now, I'm going to show you something a little mind-bending, so hang on to your hats. What if I say L2 is equal to L1, and then I say L1 sub 3 is equal to 777. Okay, there's no reason I can't do that. And so now, of course, if I print out L1, what do you think we're going to see? Well, let's find out. Sure enough, element 3, it changed from 4 to 777. No surprises there, right? That's exactly what I believe we expected to see. But now let's print out L2. What? Can anybody explain what just happened? Here I set L1 to be this, and I set L2 to be equal to L1. I changed L1, I didn't change L2, but L2, in fact, let's do this. Let's try to mix it up even more. Notice I change L2 and it's reflected in L1. I change L1 and it's reflected in L2. What the heck's going on? Does anybody have any hypothesis here?
Because you set L2 to L1, if you change something in one of them, it'll be reflected in the other one, I think.
Right. And what's really happening here, and this is important to understand, what really is happening here is we've talked about a little bit how Python is made out of objects and data is stored in objects. And L1 isn't this list. L1 refers to that list. When I say L2 is equal to L1, basically we have two things that refer to the same thing. So we're not really changing both of them. We're only changing one thing. It's like we have something with two different names. L2 and L1 are different names for the same thing, right? It's kind of like, you know, you can have two names, right? You can have your, like I have two names. My name is Jem and my name is James, but they still refer to the same object, me, right? And I can also be called Professor Scon. I can also be called Scon, right? And, right, all of these refer, these are all equal to the same object, me. All right. Now, what if I don't want to do that? What if I actually want to make a copy of L2 of L1 instead of referring to L1? It turns out there's a little trick I can use. Notice when I do this, what it's bizarrely saying, anytime you do a slice, you're making a copy instead of referring to the object itself. So if I say this, L2 is now going to be a different copy. It's going to be a whole new object. Watch what happens when I run this. It'll run. Of course, it's going to hang on me now. Come on.
Mr. Scott, I have a question.
Yeah.
I was wondering, with like not making a copy, but if you were to just like L2 equals L1, like when would that be useful and not just confusing in a program?
It's a good question. And I guess it turns out that it's useful when you want to pass things around and you want to call them by different names in different places. Like for example, when you pass something into a function, that's really two things pointing to the same thing. We call that aliasing, just like a person can have an alias. I'm gonna have to refresh this. Like a person can have an alias. See now, when we run it, notice that L1 has the 777 in it, L2 has the 13 in it, right? So again, to answer your question, sometimes we want to send people a copy of something because we want to start afresh, and sometimes we want to send somebody the object itself because they might want to manipulate it while they have their hands on it. Okay, so this is actually very important in computer science, is the difference between referring to an object, basically referring to an object and actually being that object, right? And so we're dealing with, we call these references. So L2 and L1 both referenced the same thing, but then when I did this, L1 and L2 reference or refer to two different things. And again, so they're not aliases of the same object. And again, the reason we do that is because we might want to pass the same object around and not make lots and lots of copies of it. That has two problems. When we make lots of copies of things, there's two problems. One problem is inconsistency. What if, there's an object that has information about your student records at Kenyon? Well, let's say you make a copy of that object and you change your GPA because you got a good grade and your GPA goes up, but there's another copy that still has your old GPA. That's inconsistent, right? If you have lots of copies of things, they may not all be up to date, and that can be a problem. And so if you only have one copy, if you keep that up to date and you don't mess with anything else, it's always correct. Okay, so consistency is one of the reasons we do this. Another reason we do this is memory usage. If we make lots and lots of copies of things, it uses more and more memory. Every time we copy it, we use more memory, and then we copy it again, we use more memory. Eventually we run out of memory, right? And although memory seems almost unlimited these days because we have so much memory in our computers, it's ludicrous. I mean, I have a laptop with 32 gigabytes of RAM. It's a ridiculous amount of memory, right? But still, it can eventually run out. Okay. So let me talk a little bit about something that we didn't look at last time. List functions. It turns out that lists, we saw how we could do a sort. And it turns out that there's another way we can sort in reverse, is we literally can say reverse equals true inside the sort. So here if I sort this, orange, mango, kiwi, pineapple, banana, it sorts it in reverse order. Whereas up here, if we sort it without that, it's going to sort it ascending from low to high, right? So it turns out that there's another thing, kind of cool thing we can do with our sort. We can actually pass the sort a function that does the comparison for us, which may seem kind of weird. So what we're gonna pass the function, we're gonna pass this function to the sort and say, for every value in here, I want to sort it according to how close it is to 50. So I'm going to return the absolute value of 50, and that's what I'm going to sort. So when we sort it, notice that the numbers that are closest to 50 are first, and the farther they are away from 50, it's kind of a funny trick, okay? So another thing we can do with sorting is we can apply a function to do a case insensitive sort. Now notice I have lowercase and uppercase mixed in here, and when I sort it, the uppercase always comes first because that's the way uppercase letters are, and so it's not really in sorted order the way we want it. If we want it to actually be sorted based on their alphabeticalness with it, ignoring the capitalization, what I can do is I can add a thing key.string equals lower, and what it does is it says before doing the sort, just like up here when I basically called this function on everything before I did the sort, here I'm calling the lower function, the string lower function on everything, and so when I sort it, it sorts it in order, even though it doesn't change the strings, right? When it's doing its comparison. So what this is really saying is go ahead and sort it, but go ahead before you do the comparison and do a lower, call this function on each string before you do the comparison. We already saw the reverse, right? We can take a list and we can make it go in the opposite direction. That's useful sometimes. Now there's another way we can copy a list. So we already saw, we talked about this earlier. So if we take a list, call it this list, and we make another list called my list, and here we're using a pop. What does a pop do to a list? Does anybody remember?
It takes out the last element.
Right. So here we're saying pop one thing off the list. And if we print both lists, we notice banana, we said pop one, so we're popping element number one. So we're popping it off of both lists because they're the same list. So again, the solution is, there's two types of solutions. There's the solution that we saw earlier where we use the brackets and the colon. The other solution is to literally say copy. Dot copy is a function, and if we say this list and then we say my list is equal to this list dot copy, my list is a new version. So when I pop element one off of my list, it doesn't pop anything off of this list because this list is a different list. We copied it. So that's another way to do a copy. Turns out you can also make a copy with lists. There's a bunch of different ways you can make a copy. If I say list is equal to list, this list, it takes this list and makes a new list. Now, what if I have two lists and I want to put them together? Well, we saw this in the quiz, right? It turns out we can just use plus to combine two lists. Now, another way we can do it is we can actually use append. Here I have list one, here I have list two, and instead of appending an element, if I append a list, It may seem like it would put that list at the end of this list, but it doesn't. It actually just takes that list and extends it with the second one. Extend is another option, does the same thing. I don't know why they have so many different ways of doing the same thing, but the Python people are kind of crazy, and that's what they did. So here's a bunch of list methods that may come in handy, and I'm not gonna read through them all, but you might want to keep these in mind, right? And play around with some of these. Final thing I'm going to show you in the last few minutes, as I promised, was, oh, no, that's not right. I thought I changed that to something different. Yeah. No, yeah, okay. You might have to refresh because I had it pointing to something different. List comprehension. List comprehension is something kind of weird and kind of cool. And to start with, we can make a list out of a range. By the way, a range is a list. So if I say list and a range, I can make a list. Let's try that one. So if I say list L1 is equal to list, I have to say list. So I have to turn it into a list. Range 1:30. I don't know why it's, oh, 1:30, sorry. If I print L1, notice I get a list of the numbers between 1 and 30, right? So, oops, this is where we're at. So it turns out that list comprehension is something that allows us to build lists in cool ways. So let's look at something here. So I'm going to take this. I'm going to do this code over here rather than, I should make a collaboratory out of this. Say we have this list, and let's say I make list 2 is equal to, what I want to do is this. I want to use a for and an in. I'm going to say for L, for element, and again, what I'm going to do is I'm going to say, I'm sorry, yeah, for element times 2, for element in list li. Print li2. Now what this is going to do is make a list that's double this list. Now what are we doing here? This is saying I want to build a new list, and the way I want to build a new list is I want to, for every element that's in the original list, I want to multiply it by 2. I can do anything I want. I could do multiply it by 3, and I get a different set of numbers. I could do something like this. I could do cube it, get big numbers. I could do cube it minus 1, right? So what it's doing is it's saying for every element in the list, do this modification. So that's kind of cool. This is called list comprehension, and it allows us to take a list and do, in this case, do something to every element in the list. And so the way we do it is we say expression for name in list, and what happens is this expression should contain name, and it should do something. So in fact, we could do something with strings. Watch this. I could have, you know, apple, orange, peach. Okay. And what I could, obviously this isn't going to work because I can't add numbers, but watch this. I could do this. I could say Now this is going to kind of screw up because, and you'll see why. What if I say is equal to element? What if I say I want to try to, I want to try to add an S to everything. Apples, oranges, and peaches. Of course, that's not how we spell peaches. We put an ES. Well, it's close, right? So we're adding an S. Of course, I could have done this, but then that's not right. Cancel, right? So it's saying, hey, go through this list and do something. In fact, I could do this. I could say element 0:1 to just get the first two letters of everything. I'm sorry, that only gets the first letter. We'll do this. And we get A, P, O, R, and P, E, right? So we're saying for every element in that list, do a slice on the element and make a new list. I could pick things in the middle if I wanted to, for some reason. P, P, R, A, and E, A. Or I could get the last letter in every list, right? I could say -1, and that should give the last letter. Yep. So this is pretty cool. List comprehension. You comprehend. And so I think I'm done. There's more of these that you can play around with and try yourself, but I just wanted to sort of raise your consciousness so that you could see there's some cool things you can do. So I think we're done for today. So have a good rest of the day. It's actually pretty nice outside, so maybe you can get outside and enjoy the weather. And I will see you on Thursday, or hopefully I'll see you in office hours tomorrow.
Thank you.
Okay,
Thank you.
see you later.
Thank you. Have a good one.
Bye-bye.